Okay, I'm started recording already. Good morning. So welcome back to part 3 of the topic on metals. So today we'll be going through extraction of metals. So what does this actually mean? Okay, so we shall see what extracting metals means and how do we actually extract metals on an industrial scale. All right. Now, as mentioned previously, whatever here will build on the foundations of what we have covered. We have covered redox, we have covered the reactions of metals and the reactivity series. So if you have not watched those videos, please go back to the redox and metals playlist. Finish watching all the previous videos to ensure you understand it. All right. Now, as you can see, the number of learning outcomes not too many here. Okay, there are literally just 4 learning outcomes here, divided into, broadly speaking, 2 sections. The first section is on extraction of metals. Okay, so you will see that the ease of obtaining metals is related to the position of the metal in the reactivity series. Meaning, at the end of today, you must be able to tell me more reactive metals are more difficult to extract. Less reactive metals are easier to extract. Okay, that is the learning outcome that we hope to get and we hope to be able to explain at the end of today. Now, besides that, at the end of today, we will also be looking at a specific metal, which is iron. How do we extract iron on an industrial scale? All right, so this is not just something done in the lab. You're extracting iron on an industrial scale to get tons and tons of it. And the main reason is because iron is a very useful metal for construction, okay, for other things, including making your electrical appliances that you are familiar with in your lives. Okay, so we need to know how to extract iron on an industrial scale. And if you look at the paragraph, the short text below, okay, really the extraction of iron is closely related to politics, is closely related to how countries have developed. Okay, many of us now think that Korea is very rich. South Korea is very rich, and South Korea is a powerful country, politically, economically, and culturally. Okay, so all of us are familiar with K-pop, Korean entertainment. Most of our entertainment has been taken over by Korean shows, Korean programs, right? How did it become like that? Was Korea always this rich? Well, if we just look back about 60 years ago, okay, currently it's 2022. If you look back 60 to 70 years ago, in the 50s and in the 60s, South Korea was very poor. All right. South Korea was a very poor country. Largely speaking, most of the population was farmers. All right. They didn't earn a huge income. So how did South Korea transform itself from a farming agricultural economy to what it is today? Okay, a major part of their economic strategy in the 60s was to develop heavy industry. Heavy industry are things like shipbuilding. Okay, they made ships, big ships, those container ships that float on water, that can transport goods from one point to another point. So shipbuilding was a major part of the South Korean economy. Besides that, they invested in steel making. All right. So if you go to South Korea today, you can still see a lot of steel plants. Obviously, we have learned steel is an alloy of iron. This means that South Korea had pursued a strategy of extracting iron and then taking the iron to make steel alloys. And this was useful because steel alloys allow you to make ships, they allow you to build construction like buildings and everything. So that allowed South Korea to develop really, really quickly. Okay, and we have to remember that South Korea in the 1950s and 60s had just came out, okay, of a war with North Korea. Okay, so essentially, if you think about it, the transformation of South Korea is nothing short of huge, okay, and a very big transformation. And of course, okay, if you look at South Korea today, they are rich because of this, because they had chosen the economic strategy of extracting iron and using it to make steel. And that's what we will study today, okay, in today's lesson. Okay, so now remember, in fact, most of the entertainment companies in South Korea, they have links to the big industries that make steel. Some of them, in fact, okay, started off as construction companies and then they branched off into entertainment in the late 90s and also in the year 2000 and so on. Okay, so iron extraction is a major reason why South Korea was able to become powerful today. Okay, now if we go to the next page, okay, page 2, reactivity series and the ease of extraction of metals. So that's what I was mentioning just now. Whether the metals are easily extracted or not depends on its reactivity. Okay, now most metals are able to react with oxygen, okay, to form compounds. Now, why specifically oxygen? If you think about it, well, the air around you is 21% oxygen. So oxygen is relatively plentiful and abundant, and therefore the metals can react with oxygen to form compounds called oxides. So it is very unlikely that the metal exists as an element on its own. Most of the time, the metal would have reacted with oxygen to form oxides. And where are these oxides found? Well, these oxides are found in nature, in rocks. And these rocks are called ores. O-R-E-S. So ores are rocks containing metals and metal compounds, of course. So there are many different types of ores around us. Okay, so this is extra. The table shows you the names of the ores and what is the metal compound present in the ore. So this is extra information. I don't expect you to memorize the names of the ores. However, the first one, iron. So iron is mainly found in an ore called hematite. Okay, and hematite, the rock hematite, contains iron 3 oxide. Okay, so I repeat, the ore is a rock. In the case of iron, iron is found in hematite, which is the rock, right? Hematite contains what compound? Hematite contains iron 3 oxide. Okay, so the first one you should learn. Now, I've given you other examples like zinc and copper. So zinc is found in a variety of rocks. Copper is also found in a variety of rocks. You realize that not all of them have combined with oxygen. Some of them have combined with sulfur. Okay, in fact, if you look at copper, copper has combined with sulfur in many different ways. So why? Why is it that it has combined with sulfur? Where does this sulfur even come from? So those of us taking geography, you will be familiar, okay? Sulfur is an element that is mainly found in volcanoes, okay? Volcanoes do emit a fair amount of sulfur. This can be in the form of sulfur dioxide gas. It can also be in the form of the element itself, sulfur, all right? So actually many of these rocks, many of these ores containing sulfur compounds are found near volcanoes. And that's also one reason why people still choose to live near volcanoes, even though they are dangerous. Because volcanoes, the soil is fertile. Besides that, around the volcanoes, you can find a lot of ores that can be used to extract metals from. So you will find that there's a whole industry, involving extracting copper, and these are usually located around the volcanoes. All right. Now, obviously, these are rocks. Ores are rocks. Rocks are found in mountains, caves, maybe underground. So you have to mine them out. How do you mine? You basically have to have some equipment to help you remove the soil until you can get to the rock itself. Okay, so you can imagine now this whole process of mining requires you to remove soil, requires you to remove trees, because if you don't remove trees, how do you get to the rock below? Right? So this creates a lot of problems. Mining creates problems like deforestation. Okay, besides that, when you remove the trees, the soil becomes loose because no more tree roots to hold the soil in place. So when it rains, the soil can be washed off, that causes landslides. So mining itself is a very, very bad activity for the environment. Okay, now after mining the rock out, you still have to concentrate the metal ore, right? So if you look at the process here, you got to remove the earth, you got to remove the rock, okay? Then after that, you extract the crude metal from the ore. Now, extracting the crude metal, there are two methods. You either reduce it with carbon or you use electricity. All right, so these are the two methods we will talk about very soon. Okay, and finally, after you extract the crude metal, you still need to purify and refine it further in order for it to be used in industry. All right, so this is the process, mining, from mining all the way to extracting. And this is an important process. Without this process, industry would not function. Without this process, your economy cannot grow. Okay? So let's look at the two methods we talked about. So how do you extract metals from ores? This is page number 3, and this is an important page. We will spend quite long talking about this page. Now, in order to extract metals from ores, there are two possible methods. One, using electrolysis. Electrolysis, the electro, of course, refers to electricity. Now, what does lysis mean? Lysis means to break down. So we are using electricity to break down the metal compound. We are using electricity to decompose the metal compound back into its elements. All right. Now, this is a very energy intensive process. It requires loads of electrical energy to be supplied over a long period of time. So this is always an expensive method. So let's write it down. This is expensive. All right. Electrolysis is always an expensive method. So we do not use electrolysis unless we have no other choice. So when do we use electrolysis? We use electrolysis only to extract very reactive metals. So the most reactive metals like potassium, sodium, calcium, magnesium, these metals are extracted exclusively only using electrolysis. You cannot use any other method to extract potassium, sodium, calcium, and magnesium, as well as aluminium. Okay? So even though it's expensive, we still use electrolysis to extract sodium and so on. Now, for the less reactive metals, we can just reduce their ores with carbon. Now, this is a reaction we have learned in part 2 of the metals notes. You have learned that certain metal oxides can be reduced by carbon. Okay, so let's see and let's revise. So I've shown you the reactivity series here from potassium, most reactive at the top. Now, when we say that something is the most reactive, it means that it is also the hardest to extract. It will require the most energy to extract potassium from its compound. Now, why is that the case? Now, that is the case because potassium is so reactive. Once it forms a compound, it has very strong forces of attraction present in the compound. All right. So compounds of potassium have very strong forces of attraction. As a result of that, you need a lot of electrical energy to overcome and to break down the forces of attraction within these compounds. Okay, so you can see here, very reactive metals are above carbon in the reactivity series. If they are above carbon in the reactivity series, they are very reactive, cannot be reduced. So I want you to circle these phrases and you must link them together. Very reactive, above carbon, cannot be reduced by carbon. Okay? And as a result of that, because they cannot be reduced by carbon, these very reactive metals must be extracted using electrolysis, even though it's expensive. Okay, next, how about those metals below carbon in the reactivity series? Well, if they are below carbon, we have learned in the previous part, the oxides of these metals can be reduced by carbon. Okay, so if they are below carbon, they can be reduced by carbon. So for example, we can use carbon to reduce zinc oxide to zinc. So if you look at the equation below, okay, at the bottom of page 3, I've shown you if I were to put carbon together with zinc oxide and heat them together, I will be able to reduce zinc oxide to zinc. All right. Now, how do we explain this in terms of redox? Well, we can always start out by giving the oxidation states of the elements, right? So we start with the metal. So zinc in zinc oxide, the oxidation state is +2. How do I know it's +2? Because I have to remember one of the rules in oxidation states is that oxygen has an oxidation state of -2 in its compounds. So in zinc oxide, if oxygen is -2 in zinc oxide, zinc must be +2. All right. Next, how about zinc at the end? Well, zinc at the end is an element. It's not combined with anything else. So the oxidation state is 0. So we can say that zinc oxide is reduced as the oxidation state of zinc decreases from +2 in ZnO to 0 in Zn. Okay, so let's take this down to ensure that we still remember how to explain things in terms of redox. Okay, but we remember the term redox, right? Redox means there must be reduction and also oxidation in the same reaction. So if zinc oxide is reduced, what is oxidized then? So if you look at it, if zinc oxide is reduced, the one that is oxidized must be carbon. The other reactant is oxidized. So let's try to work out the oxidation states of carbon. Okay, so now I've written in purple, carbon, where it is. Let's try to work out the oxidation states of carbon. So if you look at it, carbon at the start is an element as well, right? It's just C. It's not combined with anything else, so it's an element. If it's an element, the oxidation state by definition is 0. So at the start, the oxidation state of carbon is 0. But how about at the end? At the end, it forms carbon dioxide, CO2. And we already know the oxygen must be -2. There are 2 oxygens in CO2 though. So if each oxygen is -2, 2 oxygens will be -4, which means that carbon should be +4. So the oxidation state of carbon in CO2 is +4. And so we can come to the conclusion, carbon is oxidized as the oxidation state of carbon increases from 0 in C to +4 in CO2. Okay, so let's take this down quickly as well. Now, at this point, if you are still not familiar with how to calculate oxidation states, if you are still not familiar with explaining this, please go back to Redox, the video lesson 2 involving oxidation states. So we can see that zinc oxide is reduced, whereas carbon is oxidized in this reaction. And this reaction is possible because zinc is below carbon in the reactivity series. Because zinc is below carbon, carbon can reduce zinc oxide to zinc. Now, to add on to our understanding of redox, so we have learned how to calculate oxidation state. We have learned how to use oxidation states to explain whether something is reduced or oxidized. Now, we have also learned what is a reducing agent, what is an oxidizing agent, right? So a reducing agent reduces other things. It causes other things to be reduced. So the reducing agent must be itself oxidized. And hence, carbon is the reducing agent. How do I know that carbon is the reducing agent? Because carbon is itself oxidized. On the other hand, zinc oxide is the oxidizing agent. How do I know that? Because zinc oxide is itself reduced. Okay. So at this juncture, you can start to see how redox is very, very relevant when we talk about extraction of metals. Okay, for those on the Zoom meeting, if you're done copying and if you have no more further questions regarding this, can you give me a thumbs up so that I know? Okay. Ken? So this is an example of how a metal could be extracted using reduction with carbon. Basically, you take the oxide and you heat it with carbon. That gives you the metal and carbon dioxide gas. All right. Now, this method doesn't just work for zinc. It works for all metals below carbon. So zinc, iron, lead, copper as well. Okay, they can all be reduced with carbon. So these metals below carbon will be extracted by reducing their oxides with carbon. And in all these reactions, carbon is the reducing agent. Okay? So I repeat, there are two groups of metals. One, those above carbon. Those above carbon, they are very reactive, so they cannot be reduced with carbon. You need to use electrolysis for the very reactive metals. The second group is the group below carbon. Those metals below carbon in the reactivity series, they are not so reactive, so they can be reduced by carbon. All right. Now, there's one last exception. Now, gold is right at the bottom of the reactivity series. Bottom means very unreactive. So gold is one of the least reactive metals around. If it's least reactive, it means that it's very easy to extract. It requires very little energy to extract it. Now, gold is so unreactive that it doesn't even react with oxygen. So you can have gold in the soil and it will never react with oxygen, even after thousands of years. So gold is one of the interesting elements. Gold is one of the interesting elements because it exists as an uncombined metal, or the native element. Native element means it has not combined with anything else. So gold can easily be found on its own, uncombined, native in the soil. So how then do you extract gold? Well, all you need to do is to find the gold. Gold is usually found in the river bed, bottom of the river. So you go to the river bed, then you find the gold. Then what must you do? Oh, it's still together with sand, right? It's a mixture. It's mixed together with sand, with water. It's a mixture. It's not a compound. So how do you separate mixtures? Well, you can use your physical methods of separation. So gold is usually separated from sand and water using filtration. So all you need to do is to do filtration. Okay. for the sediments found in the riverbed. Now, this filtration is not just your normal filtration, okay? It involves sorting the sediments by weight, all right? Gold is heavier than sand, so gold tends to settle to the bottom. So by doing filtration by weight, you can get gold right at the bottom. Then you must be wondering, hey, if gold is so easy to extract, I don't even need to use heating, I don't need to use any chemical reactions, I just need to do filtration, right? If it's so easy to extract, why is gold still so expensive and valuable? Because whether something is valuable or not doesn't just depend on how easy it is to extract. Gold is valuable because it's rare, okay? Although I say it's easy to extract, gold is rare. It's very difficult to find gold. In the whole river, maybe there's only a few sediments that are gold. The rest of it is just sand, all right? So because gold is so rare, that's why it's expensive, not because gold is difficult to extract, all right? Okay, so this page, I hope you know the trend by now. Most reactive, difficult to extract, electrolysis. Those below carbon, less reactive, can be reduced by carbon. Finally, the last one, gold. Gold is so unreactive, doesn't react with oxygen. Therefore, it is uncombined. Okay? And we have also gone through the redox reaction involving reducing the oxide with carbon. You must make sure you can explain this in terms of redox. All right. Now, there are a few questions here, which I will not go through now. I will go through them when school starts, when I teach this in class again, but I would like you to try it. So as you can see, the first question is a typical essay question. Now, the first question actually wasn't taken from the pure chem exam. The first question was taken from the combined science exam. So for combined science students, they have a lot of these essay questions at the back of their paper. So this is what I make my combined science students do every single year when we get to this topic. Okay, so it's just explaining using examples what we have explained just now. How come some metals are uncombined? How come some metals, the oxide, you can reduce it with carbon, some other oxides you can't reduce it with carbon. So this one, try it yourself, please. Then we go to question 2. Now, question 2 is an interesting question. Okay, it tells you when the metals were discovered first, right? So you can see that, oh, maybe there's a trend between the reactivity of the metal and when it was first discovered. Okay, you can clearly see that some metals were discovered a long time ago. Copper, 7,000 years ago, right? Whereas sodium was only discovered 207 years ago. So there must be some relationship between the reactivity of the metal and when it was first discovered. All right. I've also given you the abundance of the metal, right? Abundance is how much of the metal do you actually have on Earth. So you can see that gold was discovered a long time ago, 8,000 years ago. However, gold is valuable because it's very rare. You can see that 0.0011 is a very, very low abundance, very rare. Okay. Now, I shall leave you to do question 2 on your own as well. For now, I want to try the MCQ question 3. Now, this is on page 6. At the bottom of page 6 of the notes, I want you to do it now and let's go through it together. All right, read carefully. Okay, so let me just give you 1 minute to read through question 3. Okay, as you read through, I hope you're also highlighting phrases that are important. Okay, so you should always highlight chemical names. So metals XYZ. Please also highlight things like increasing versus decreasing. Okay, always highlight such words. Okay, finally, I hope you're also highlighting chemical names like hydrochloric acid. So from the first question, does the metal react with dilute hydrochloric acid? Yes or no, right? Okay, so you immediately know that Y doesn't react with acid. Metal Y doesn't react with acid, whereas X and Z do react with the acid, right? So let's try to recall. If the metal doesn't react with acid, what does it mean about its position in the reactivity series? So we have to think back to the previous set of notes, part 2, right? Where we learn about reactivity series, the reaction with acids. Okay, so which metals don't react with acid? So you think, copper doesn't react with acid. Silver, gold, they don't react with acids. How do we know that? Because if it doesn't react with acid, it means it's below hydrogen. Metals below hydrogen do not react with acids. Therefore, if it's below, that means it's unreactive. That means of the 3 metals, X, Y, and Z, Y must be the least reactive. So based on the 4 options, least reactive must be Y. So immediately B is wrong. D is also wrong. It's either A or C, right? We have eliminated options B and D because we know that metal Y must be the least reactive because it doesn't react with dilute hydrochloric acid. Okay, now the next question. Is the oxide of the metal reduced by heating with carbon? Now, this is the crucial one. Most students will always forget this because they think that no means unreactive. But they don't read the question carefully. You read the question again. Is the oxide reduced with carbon? No. No means what? No means the oxide cannot be reduced. Right? No means that the oxide cannot be reduced with carbon. So which oxides cannot be reduced? That means metal Z is above carbon. We have just learned that, right? Metals above carbon, their oxides cannot be reduced by carbon. So in this case, no means it's above carbon. Above carbon means very reactive. So most students get tricked in the second question. Most students know the first question, but they don't know the second question. So don't get tricked. Whatever I've highlighted in blue, together with the annotations, please take down. Okay? So if you know that it cannot be reduced by carbon, this means that the metal is very reactive. And with that, we come to the conclusion, the most reactive must therefore be Z. Therefore, the answer is C. Okay, now this MCQ was not from the pure chem paper. This MCQ was from the combined science TYS. But I've chosen this question because after so many years of teaching combined science and pure chem, I do notice that it is such a question that will always trick students. Okay, so please don't be tricked. If the oxide cannot be reduced, that means it's very reactive metal. Okay, one way to remember is potassium, sodium. The only way to extract them is electrolysis. You cannot reduce using carbon. Therefore, These are very reactive metals. Okay. Okay, so once you're done with this question and you have no further questions regarding this MCQ, can you give me a thumbs up? But make sure you have copied down the annotations, huh? Okay, so we are doing good on time. We should be able to finish in the next 30 minutes or less. Now, as mentioned at the start of this topic, we're going to talk about iron, right? How to extract iron on an industrial scale. And that's how South Korea became very rich. So how do you extract iron from an industrial scale? So that's the next page. Now, you might feel that the next page is a series of facts and details, but this is a series of facts that you must learn well, memorize well, okay? Because it does come out quite often. So now we're going to learn how to extract iron metal from hematite. Remember hematite, hematite is the name of the ore, okay? It's the rock's name, okay? Now, iron metal is extracted from hematite ore in the blast furnace. Now, the blast furnace is basically a furnace, a big oven heated to a high temperature. You need a high temperature to extract iron metal from hematite. Okay, and this takes place in the blast furnace. Okay, blast furnace is basically a big oven. Okay, so let's start by filling in the table on top. What is the name of the ore? The name of the ore is called hematite. What iron compound is present inside hematite? Iron 3 oxide. Formula Fe2O3. Remember, the 3 in this case refers to the oxidation state on iron. It means that the oxidation state of iron is +3 inside iron 3 oxide. Okay, so the next two questions, I'm going to guide you along. What are the impurities in hematite? Now, hematite obviously is a rock, right? It's a rock. The rock is not pure iron 3 oxide. Rocks, rocks along the road, obviously it's not going to be pure. It's going to be a mixture of different things. So similarly, hematite must contain impurities. It's a rock. Most rocks, the main impurity is silicon dioxide. How I know this? Not because I memorized. It's common sense. Silicon dioxide is what makes up sand. Okay, so the sand you see is basically silicon dioxide. Okay, now sand, silicon dioxide has a giant molecular structure. I hope you remember that. Okay, how do I know the rock must have sand? Because rocks typically contain sand particles in them. Okay. Okay, what are the raw materials added into the blast furnace? There are 3 of them. The first one, obviously, is hematite. No hematite, obviously no iron to talk about, right? Now, the second raw material is called coke. But this is not the coke that you drink. No, coke is basically carbon. Okay, carbon. So why don't we just call it carbon? Because you already know by now, carbon comes in many different forms. Carbon can be in graphite, carbon can be in diamond, carbon can be in charcoal, carbon can also be in coke. So what is the difference? Coke typically is like charcoal, but it's more finely powdered. Okay, so coke is basically like charcoal, but more finely powdered. Okay, so always write coke, don't write carbon, because carbon is too generic. You won't be adding diamond to extract iron, right? That's too expensive. Okay, the last raw material, important, limestone. And we will talk about limestone in a short while later on. Okay? What is the purpose of adding limestone into the blast furnace? So we'll leave it first. Later, we will come back to this. But these are the three raw materials that you add into the blast furnace: hematite, coke, limestone. Okay, so there's a series of 5 steps. Each of it comes with blanks to be filled in. You need to fill it in, or else you wouldn't know how to write the essay. Okay, for my combined science students, I always tell them you need to memorize this because this could become your essay question. And every year it does come out. So my combined science students who study this obviously will do well. Okay, having said that, okay, for pure chem, of course, you have so many other things to test. So they may not test this in the essay. Nonetheless, you should know the reactions well. Okay, so there are 5 reactions. We're going to divide it into step 1, 2, and 3, one group. Step 4 and 5, another group. We will explain why later. Okay, so step 1, coke. Coke is carbon, right? Coke reacts with oxygen in hot air. This produces carbon dioxide gas. The equation is very easy to write. Coke is carbon, so it's solid carbon, C bracket S. C plus O2 forms CO2. Okay, so where does the oxygen come from? The oxygen comes from air, right? Inside the blast furnace, there's air, okay? And the air is heated to a high temperature. So this reaction happens. And this reaction forms CO2, simple. Step 2, carbon dioxide from step 1 reacts with excess coke to form carbon monoxide. Now this is crucial. Step 2 is crucial. You don't actually want CO2. What you want is to form CO, carbon monoxide. Okay? So the whole purpose of step 2 is to form carbon monoxide. Why? Because in step 3, carbon monoxide reduces iron trioxide in hematite. And this helps you to form molten iron. The molten iron would sink to the bottom of the furnace. The equation for this, iron trioxide is a solid plus carbon monoxide gas. Now this forms molten iron. Because it's molten, you must know the state symbol is liquid. Okay? Okay, once you're done with copying these equations, can you please give me a thumbs up so I know I can continue? Okay, when copying the equations, make sure you copy the state symbols in because the exam question may ask you for the state symbols. Okay, now, so I mentioned just now, right? Step 1, 2, and 3, we will take it as one group. Why? Because the first three reactions here, they are meant for you to extract molten iron from hematite. So the whole purpose of the first three reactions is to extract the iron. Okay? Now, besides that, the first three reactions have something in common. They are all redox. The first three reactions are all redox reactions. Step 1 is redox. Step 2, also redox. Step 3, definitely redox. Okay, so steps 1, 2, and 3, they are all redox reactions, which means that you may be asked to explain what is reduced, what is oxidized. You may be asked to work out what is the reducing agent, what is the oxidizing agent. And that is what we are going to do for step 3. Now, for step 3, you realize that the equation is relatively difficult to balance. Why is it difficult to balance? Because you got to have 3CO2 Fe 3CO2. So for step 3, the equation, I strongly recommend you try to memorize it. All right? Because trying to work out how to balance it may take you time. Okay? Now let's just focus and home in on step 3. I want you to work out what is reduced and what's oxidized. The simple way to work it out is always to start from the oxidation state of the metal. Always start with the metal first. Okay, the metal in step 3 obviously is iron. So let's work out the oxidation states of iron at the start and at the end. So in Fe2O3, at the start, the oxidation state of iron is +3. How do I know that? Because oxygen is -2. I have 3 oxygens. 3 times -2 is -6. Therefore, each ion must be +3. Okay? So at the start, the oxidation state of iron in Fe2O3 is +3. At the end, iron is an element. By definition, elements, the oxidation state will be 0. So it's quite clear Fe2O3 is reduced. All right? Fe2O3 is reduced because the oxidation state of iron decreases from +3 in Fe2O3 to 0 in Fe. All right, so let's take it down quickly at the sides. Okay, there may not be a lot of space, but on your paper, there should be more space. So let's take it down quickly. Fe2O3, let me write nicely. Fe2O3 is reduced as the oxidation state of iron decreases from +3 in Fe2O3 to 0 in Fe. Okay, so iron 3 oxide, Fe2O3 is reduced. So now, unsurprisingly, it's redox. So if something is reduced, something else must be oxidized. So what is oxidized in step 3? So again, we work out using oxidation states. After the metal is done, we should work out the oxidation state of the non-metal. The non-metal in this case meaning carbon. We do not work out oxidation state of oxygen because oxygen is usually -2 in the compound. So we should work out other non-metals like carbon. So carbon is present at the start in CO, carbon monoxide. So what is the oxidation state of carbon in CO? It's +2. It's +2 because oxygen is -2, so carbon must be +2. So at the start, carbon is +2, it goes to +4 in CO2. So we can conclude that carbon monoxide is oxidized as the oxidation state of carbon increases from +2 in CO to +4 in CO2. Okay, so let's take this down. And with this, you have learned how to combine redox together with extraction of iron. All right, and it's quite clear from this as well. Therefore, CO, carbon monoxide, carbon monoxide is the reducing agent. It's the reducing agent because it's itself oxidized. Okay? And this is the reason why I hope you will revise redox because you can see this is where a lot of things can combine together. Okay, so with that, we have finished steps 1, 2, and 3. We have also explained step 3 in terms of redox. We have also explained how you can work out that carbon monoxide is the reducing agent. So the reducing agent in the blast furnace is CO, carbon monoxide. Okay, the reducing agent is carbon monoxide. So if you are scared you'll forget, you can highlight. CO is the reducing agent. Okay, so once we are ready with this, you've understood it, you have no further questions, can you please give me a thumbs up? Then I'll finish the last 2 reactions. Okay, great. Let's move on. Now you might be thinking, so why do we need to have 2 more reactions? Don't we already have iron? Isn't the objective already met? I got iron, right? From the blast furnace. At the end of step 3, you already have pure molten iron. You have the molten iron, is good enough. However, remember, it's from hematite. Hematite is an ore, it's a rock. The rock contains impurities. The main impurity is silicon dioxide. All right. As a result of that, you must get rid of the silicon dioxide. If not, it will contaminate your molten iron. So how do you remove this silicon dioxide impurity? Well, you need to use limestone. Now, what is limestone? If you recall, limestone is calcium carbonate. Limestone is calcium carbonate. Now, calcium carbonate will decompose when heated strongly. Now, if you recall, this will form the oxide and carbon dioxide gas. Oops. Now, we have learned this under decomposition of carbonates, right? Carbonates decompose to form the metal oxide and carbon dioxide. So limestone is calcium carbonate. Calcium carbonate decomposes to form calcium oxide and CO2. Now, it is the calcium oxide that we need. Calcium oxide will react with other rock minerals, including mainly silicon dioxide. Now, calcium oxide reacts with silicon dioxide to form calcium silicate. The formula of calcium silicate is this. Okay, let's write this down. This is calcium silicate. Now, the simpler word is just slag, S-L-A-G. Now, it's also molten because it's very hot in the blast furnace. So it will be produced as a molten compound. Okay, so what is molten slag? Molten slag is calcium silicate, CaSiO3. Now, this is convenient because what you have done is you have taken the silicon dioxide impurity, you have reacted it away. Because you have reacted it away, it forms calcium silicate. Now, calcium silicate floats on top of the molten iron. So because it floats on top, it doesn't mix. That means you have removed it from the molten iron. Doesn't mix, right? It's like oil floats on water. So the oil and water don't mix. Similarly here, the slag, the calcium silicate, which is called slag, the slag floats on top of the molten iron, so they don't mix. So what is the purpose of doing this? Now, you will see in step 5, step 5, you have calcium oxide, silicon dioxide. They are both oxides. So you got to remember, when did we learn about oxides? Well, you learn about oxides and types of oxides under acids and bases, right? So you have learned calcium oxide. Calcium is a metal. So calcium oxide is a metal oxide. Metal oxides are basic. So calcium oxide is basic. On the other hand, silicon dioxide. Silicon is a non-metal. So silicon dioxide is acidic. Which means that step 5 is not redox. Step 5 is an acid-base neutralization. The acid is silicon dioxide, it's an acidic oxide. The base is calcium oxide. All right, so step 5 is not redox, it's acid-base neutralization. So this is the reason why we have separated out the 5 steps into 2 groups, right? Steps 1 to 3, redox. Step 4 and 5, not redox. So the last 2 steps, the last 2 reactions are for removing acidic impurities. What is the acidic impurity? The acidic impurity is silicon dioxide or sand. All right. So we basically remove the acidic impurity of silicon dioxide from the system using step 5. Okay, so if you are done with copying this down, can you give me a thumbs up so that I know you're done? Okay, great. Now you realize there's a lot of detail on this page. This one single page contains loads of detail which has to be remembered. So this is why we spent a lot of time on this. Now let's go back to the top of page 7. So just now I mentioned to you, right? There are 3 raw materials you add into the blast furnace. Number 1, hematite. Number 2, coke. Number 3, limestone. So what is the limestone for? The purpose of adding the limestone is to remove acidic impurities. The acidic impurity is silicon dioxide from the hematite and the molten iron. Okay, so the purpose of adding limestone is to remove acidic impurities. Now, this is quite commonly tested. The purpose of adding limestone is to remove the acidic impurities. Okay, with that, we have actually finished what we wanted to cover today, which is how do you extract iron through different reactions in the blast furnace. So these 5 reactions must be learned. including the equations and state symbols. So you need to be able to describe it and write the equations. All right. Now, that was page 7. Learn it well. Now, let's go to page 8. Now, page 8, actually, there's nothing to copy. It's just a diagram showing you what the blast furnace looks like. The blast furnace looks like this. It's just basically an oven. It's a very big oven that's heated to a high temperature. So you can see what goes in. Well, these are your raw materials, right? The iron ore is called hematite. Hematite, coke, limestone is added into the blast furnace. All right. And the reactions will happen. And as mentioned, these reactions produce molten iron. Molten iron is at the bottom of the furnace, right at the bottom. The reason for this is because it's very dense. It has a high density. Therefore, it sinks to the bottom of the furnace. So it's very easy. You just need to open up the tap at the bottom of the furnace. The molten iron will flow out. Okay. The slag, remember, is produced from the reaction between calcium oxide and silicon dioxide. So the slag will float on top of the molten iron. Okay. Now, is slag useful? Now, slag is quite useful. It can be used in construction as well. Okay, it can be added to cement, for example. Okay. Now, these reactions together will produce some waste gases. The waste gases are mostly carbon monoxide and carbon dioxide, CO and CO2. So you can immediately imagine the extraction of iron in the blast furnace. Is it going to be environmentally friendly, or is it going to cause pollution problems? So I'll leave that for you to think. We have learned this under atmosphere. If you release waste gases like CO and CO2, what are the impacts of these waste gases on the environment? Okay. Another way to see it is in terms of a diagram like this. Your raw materials, hematite, coke, limestone. These are your raw materials. And then your products are here. Okay. Your products are slag and molten iron. Okay. Okay, so what have we gone through today? We have gone through how do we extract iron in the blast furnace. That 5 reactions. Please learn them well. The second thing we went through at the start of the lesson today is how do you relate the position of a metal in the reactivity series with how easy it is to extract. And that was on page 3 of the notes. So the key pages today, I would say page 7 for blast furnace, as well as page 3, where we went through how do you extract the metals, how is it related to its position in the reactivity series. So please revise page 3 and page 7 well. All right, and that concludes our lesson for today. Okay, thank you. I shall stop recording now.